David Smith here with yet one more flipped classroom math lesson. 3 tips before we start. First, you can adjust the playback speed faster or slower to suit your desire. Second, you can pause the video at any point to jot down questions or catch up with your notes. Third, you can turn on the captions so you can read my words on the screen. Before I start the lesson, I'd like to just take a moment to thank all of you guys for your support in helping me build my channel. I just passed 700 subscribers today, and that's just a super nice milestone. So thank you so much for all of your interest, all of your likes, all of your subscribes, and I'm just super happy that all these crazy videos that I just keep on recording are helpful, supportive, and help you guys to master your mathematics. Today's lesson covers logarithms and then their transformations. We're going to talk a little bit about inverse functions as well. So check this out. Logarithms, weirdo word for sure, but it's actually a pretty straightforward mathematical process. It's just doing exponents backwards. It's like the inverse of exponents. So logarithms are a different way to write exponents. So that's true. And then 2, they're a way to solve for unknowns in the exponent. So let's take a look at an example that's more abstract. If you have some number and it's equal to a different number raised to a power, and the power is the thing you don't know, then there's no algebraic way to do this. This is just like taking the sine or the inverse sine of an angle. You can't do that with pencil and paper. You've got to use your calculator. So if you have a equals b to the x and x is the unknown, then the way you find that unknown is you take the log base b of a, and that gives you x. And this is a calculator step. Now, a little historical note, back in the day, like 150 years ago, we didn't have calculators that did all this stuff. So they used tables. Someone laboriously worked out with guess and check the values of sine of 60 and sine of 61 and so on and so forth. And they also worked out the values for exponents for just guessing and checking to build log tables so that you could look them up in tables. And these things took years to make. And then they were used by mathematicians all over the place to take the log or take the sine or take the cosine, things like that. Now you have these little fancy little calculators that just do it in a heartbeat, those tables that are embedded inside the calculator. So let's take a look at as a problem that you might encounter, a very straightforward log type problem. So let's try something like 2 equals 3 to the x power. Now that's going to be kind of hard to do. You can guess and check that. I know it's going to be less than 1 because 3 to the 1 is 3 and that's bigger than 2. I know it's going to be greater than 0 because 3 to the 0 is 1 and that's less than 2. So I could plug in 3 to the 0.5, see what I get, and just sort of laboriously check that via guess and check. But if I need to do 3 sig figs, that's kind of going to take a little while. So what I want you to do, first step, pause the video. This part here, this equation is written in this form. I want you to write the log equivalent of this exponential equation. So pause the video, rearrange the numbers, put your log on there, and come back. Okay, so that would be log base 3 of 2 equals x. Now the way I remember how to do this is the base of the power. So this becomes the base of the log. And then the other number goes here, and the x is out by itself. So if you just remember this phrase, and actually it's in your IB formula booklet, but my guess or my hope is that by the time you've done enough of these, you don't need to look for that. You just have to remember a equals b to the x, then you're going to get log b of a equals x. So if you can just dash that out on your page, you're going to be good for rearranging log equations. Okay, second step. Now I want you to pull out your fancy calculator and do log base 3 of 2 and find out what that equals and come back. All right, so on my calculator, this is what I get. X equals 0.631. Now on most calculators, when you activate the log function, it's really straightforward. There's little spots for putting these that are totally clear. Now on my TI-84, it's not clear. It's called the log base function, and it says log base, opens with a paren, and you just have to put this one first, comma, and then the base, and then press enter. And that's where I got my 0.631. If you struggle with your calculator, just bug me in class or pop onto YouTube and look up how to do logs with my fancy calculator. Just a minute ago, I mentioned how logs and inverse functions are related. And the truth is that they are very, very much related, just like multiplication and division are related. So a log is the inverse of an exponential function. So let's take a look at how that works out, just in an abstract way. So if f of x is g to the x power, we can rewrite that as just y equals g to the x power. So that's just our function right there. Now you remember what we do when we find the inverse of that function is that we switch the x and y and we solve again for x. We're not going to quite go that far, but we're going to wind up with a log. So to find the inverse of this function, we just switch the x and y. So check this out. We're going to go x equals g to the y. Okay? Now that's the inverse. That's our inverse. Now let's solve this for y. Okay? Let's figure out the log equation that lets us find out what y is. And that would be log g of x equals y. Okay, so what this result means is that if this is f of x, then f inverse of x is this. It's log g of x. So the function, g to the x, the inverse of that function is log g of x. So pretty sweet, huh? Pretty cool. All right, let's take a look at what this looks like graphically. So some function f of x is just a constant a to the x. We're assuming x a is bigger than 1. It's going to look a little bit like this. And that point is 0, 1. We don't have any transformations going on, so it's going through the point 0, 1. So this is our f of x right there. Now, I'm hoping that you can dig back and remember how we graph an inverse, what it looks like on the graph. If you know the function, there's a really straightforward trick that you use to just sketch the graph of the inverse of that function. So pause the video, think a minute. If you want to be really diligent, dig back through notes, see if you can figure that out, sketch your graph, and come back. Okay, here's a hint. The inverse of a function is always the reflection across the y equals x line. So this is the line where just the numbers are the same. Points are 1, 1, 2, 2, 3, 3, 4, 4, and so on. So that line is a 45-degree line, and the f inverse of this is just a reflection across that. So go ahead and pause the video and sketch that in. Okay, so I just sketched my curve. I reflected it across the y equals x line, and I get this increasing function that goes to the point 1, 0. This one went through 0, 1, so this one has to be 1, 0. Now, I want you to think closely. From the graph, what are the asymptotes of each of these functions? Pause the video, write those down on your graph, and come back. Okay, you can see from the graph here that my f of x function asymptotes out to the 0 line. That really shouldn't curve up, that should just keep going straight out. So f of x has an asymptote at y equals 0, and f prime of x has an asymptote at x equals 0. We're trending right towards the y-axis, which is the line x equals 0. So there you have that. Now, one last thing. Write the function for f prime of x. What is this function? You have everything you need to do that. Maybe look up through your notes, pause the video, and come back. All right, so if f of x is a to the x, f prime of x is going to be log base a of x. That's how that works. So there is my inverse function for this graph. All right, let's look at some qualities of logarithmic functions. These are functions in this form, log base a of x. So first off, the a term. Again, The A term, so commonly in mathematics, is the super important one. It covers a lot of ground. So if A is bigger than 1, the function is increasing. And this is the graph that we had from the last board, just increasing through the point 1, 0. That's our x-intercept there. Okay, now if A is between 0 and 1, the function is decreasing. When you think real hard, what would that graph look like? Use your intuition. Just think about how you would make a decreasing function. Now remember, the intercept's going to be the same, but how would you make that decreasing? Pause the video, sketch that in, and come back. So check this out. It just decreases in the same shaped curve. We've just reflected that across the x-axis. It's going through 1, 0. And so this is f of x is log a to the x when a is between 0 and 1. Okay, so that takes care of a. When you have this function, the x-intercept is 1, 0. We've been all over that with our graph. The vertical asymptote, again, when you have this simple function, is just x equals 0. Now we're going to change that when we do transformations, but right now this is for the base log function, like the mother function. Finally, the domain is 0 to infinity. We don't have any negative numbers in our domain. The range is negative infinity to positive infinity because it just goes up as far as you want and it goes down as far as you want. So those are the qualities of log functions. Okay, now let's look at some transformations of our basic log function. So again, we're starting with log a of x, but we're going to transform it, so we're going to throw other numbers in there. So the first transformation, this is a horizontal slide. We're going to move it to the left or the right. And so what it is that if you have a number inside here, which we're calling h, should be familiar. We do this in parabolas, we do this in other functions. The h is going to move the function left or right. And again, the trick is it moves it in the opposite direction of the sign. So if this was -3, x minus 3, we'd be moving the function 3 to the right in the positive direction. Second transformation, here is log a of x, and we're adding some constant here. I've used lowercase k for that. This is just going to move the function up or down, and the sign is correct. So if it's +3, it just takes the function and moves it up 3. Finally, we have this uppercase k. If we're multiplying the whole expression by a k, what we're really doing is we're just multiplying the y value by that k. We do the log function here, and then we multiply the result by k. So what this does is it's going to speed up or slow down the increase or decrease of the function. So if k is less than 1, it's going to slow it down, it's going to soften the curve. If k is bigger than 1, it's going to sharpen up the curve, make it go faster. And then of course that depends on whether it's increasing or decreasing as to how that curve looks on the graph. One last transformation. If you have a negative in front of your log expression, if it's just negative or it's -5 or whatever, what we're doing is we're just taking the related function and we're going to reflect it across the x-axis. That's all that does. All right, I want to finish this video off by just simply doing a couple, 2 or 3 transformations in Desmos so we can quickly watch what happens to the graph. Now remember, you might get a graph question on a non-calculator portion of a test, so you're going to need to be able to sketch these graphs. But right now, I just want to explore them so you can see what's happening. So let's pop over to Desmos. So here we are in Desmos, and you can see up here in the left, I've just graphed a very straightforward log function, log base 2 of x. And here we go, we've got our log function cruising along right up there. So now what I want to do is graph another one. So I'm just going to do y equals log. Now, the Desmos understands what logs are, but if you just type log, you're going to get a base 10 log. So we need to have a different base, and you can get that through the this little calculator button over on functions. You can zip on down to the calculus category right down here, and there's log base A. But this thing is a little bit cumbersome, plus it takes a lot of clicking. I'm a fan of keyboard shortcuts. So if you're right here, all you need to do is a shift dash, and you'll notice that cursor slipped down, and we're in the base section. So I'm going to type 2. We're going to do a log base 2. But now what we're going to do is a parentheses, and we're going to do an x minus 2 plug. You can see what we've done is we've just shifted that log 2 to the right. And now our intercept is 3, 0, which totally makes sense. The other intercept was 1, 0. Now let's just try this the other way. Let's do +2. And you can see, again, we shifted it, but this time to the left in the negative direction with our +2 inside the parentheses. And let's do one more. Actually, what we're going to do, let's get rid of that. Now let's add something on the outside. Let's do +2. Now check that out. We've pushed the log function up by 2. So everywhere it was at the 0, now that's at 2. So here was our former intercept at 1, 0. Now that point is at 1, 2. You can see every point on this function is further up. Now we'll talk later about how to figure out the new intercept. Let's do one more transformation. What did we do? We added, subtracted. We also multiplied by a number out here. So I'm just going to add a 2 to that. We've steepened up the curve, increased the rate at which it's increasing. Now let's change that to 0.2. We've shallowed it out. Still going through the same intercept spot, but now it's going a little bit, not increasing quite as quick. Finally, let's go do the negative, that just to show you that one. And you can see that reflected us across the x-axis. I would encourage you to play around in Desmos or on your graphing calculator and experiment with what you can do to logarithmic functions. Now that you've watched the video, take a moment to jot down extra notes or jot down some questions for our next class. You can also re-watch portions of the video that you didn't get the first time. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.